Right, I thought I'd put this slide up first because it shows that the previous three speakers are professors and I'm just a doctor, so lower your expectations appropriately, because this is going to be a fairly bit more fun, bit more basic talk about galaxies and things, so there we go. I'm going to talk about galaxies because everybody at Nottingham does galaxies. Everybody across the road in our little hut over there does galaxies in one form or another. So you've heard from two speakers already from our department, well, one and a half. So Fraser, the first one, was my PhD supervisor, so he can vouch whether I got it or not. So that was a few years ago. So I came late to the party kind of thing and studied that. Chris Consley used to be in an office just around the corner from him, but moved to Manchester a couple of years ago. So they're all doing galaxies. So this is really Galaxies 101. So some of you may find this a bit basic, but I hope I'll throw in a few sort of curveballs here and there. So these are the sorts of galaxies that we don't study, because these are far too near and far too interesting, far too beautiful to actually study because everybody's already done them. So we typically study high redshift galaxies, which Chris and Fraser both showed you this morning as a very blobby. I did kick Chris in the shins over lunch because he stole half my photos. Well, he didn't really, but he's got half the photos I've got. He's also had in his lecture. So Hubble Ultra Deep Field, yeah, we saw that from Chris. It's galaxies all the way down. So Chris actually worked out the number of galaxies in the universe, about 2 trillion he came up with, although I got him to get it to a number that was 42 by appropriate dividing and changing units, because I thought if the ultimate answer was 42, then we'd be in a much better space. This is completely irrelevant. Just to set some context, I'm sure you all know this. These are the sorts of units we deal in. We never deal in this one astronomical unit because it's just too tiny on the scale of galaxies. So Fraser mentioned something about this in his resonances. We start at parsecs. Everybody uses parsecs in astronomy. We don't use light years. I don't know why. Light years seem a lot more intuitive to me, but parsecs is where it's at. Everybody publishes in parsecs. And a parsec is basically the distance between stars. So whenever somebody talks about parsecs, it's about the distance you have to hop from one star to the next. So that just gives you a sort of a scale of the universe. And just to put that really in context, if we shrunk the sun down to the size of a marble, so something about a centimetre across, and put it in Nottingham, this is where Alpha Centauri would be, somewhere on that circle. So you can see the galaxies are pretty empty. You have one marble in Nottingham and another almost in Calais, and the intervening space is completely empty. So galaxies can really pass through each other without actually hitting each other or doing anything like that. So what's a galaxy? Well, this is Herschel's idea of what a galaxy was. He did this by just looking out into the night sky and counting stars and saying, well, if there's more stars in that direction, it probably goes further in that direction. It's not a very good model of the Milky Way because he didn't know about things like dust, which block quite a lot of the light and stop you seeing very far. So this is what our picture of the universe looks like, at least our best guess. It's really difficult to make a map of the Milky Way while standing inside it. It's like trying to make a map of London by standing in the middle of Piccadilly Circus and seeing what you can see. It's pretty hard. It's much easier to see them from outside. Back to dimensions. So this is about 30 kiloparsecs across. So when we get to kiloparsecs, so parsecs jump from star to star. Kiloparsecs, you're starting to talk about galactic distances, how far galaxies are. Well, 100,000 light years and old money, if anybody still uses those. And great reviews on TripAdvisor, the Milky Way, 300 billion stars. That's about the number of stars that occur in the galaxy. And for a long while, nobody knew whether galaxies were part of the Milky Way or not, because you get these funny blobby things right in the middle of your picture, scattered amongst the stars. But anyway, it turns out that they are much further away than the stars, so they are island universes. And I thought I cut that picture out, but I haven't. So that's the Mount Wilson 100-inch and, what's his name, Hubble looking through it. As Chris said, he really knew how to take a photograph. He could pose with aplomb. Next distance is the megaparsec, and when you get to megaparsecs, you're jumping between galaxies. So about 1 megaparsec is roughly the distance between galaxies. So if you're talking megaparsecs, you're jumping from galaxy to galaxy, or galaxy cluster to galaxy cluster. That's about where they appear. And if you go fully up to gigaparsecs, you're talking about the size of the universe. It's about 28 billion parsecs. So yeah, 28 billion parsecs across the visible universe. So I hope that orients you somewhere. I'm going to skip over that. That's boring. So originally we had to make sense of galaxy morphology, which is just what galaxies look like. And it's another one Chris stole from me. Well, not stole from me, same idea. But so this is the different types of galaxies. We actually have 4 types. So the spiral, the elliptical, the lenticular, and the irregular. So that's basically anything that doesn't fit into the above 3. It's always a good thing to have a sort of bucket to put any galaxy that you can't fit. And this is Edwin Hubble's scheme that also Chris mentioned. So there are a few issues with this. It's quite old now, goes back to about the 1930s, and we know a lot more about galaxies. Some people, possibly even Hubble, thought it might be a sequence that you go from these to those. So these are often called early type galaxies, and these are called late type galaxies. But as Chris mentioned, it's actually more likely that these conspire to make those. And I'll show you some pictures of those. So it's very confusing that these are early type galaxies, but they're actually the later ones formed, and these are the, yeah. There's a whole lot of things. When I become emperor of astronomy, there's a whole lot of things I'm going to fix. This is one of them, magnitudes is another, and star classifications, okay? We don't need OAB, we need ABC. Yeah, if you know about spiral galaxies, then you can work out the joke there. But, so this is Andromeda Galaxy, the very nearest part of our local group. It's gravitationally bound to us, so it's always going to be with us, 2 billion light years away, so we're seeing it as it was 2 billion years ago. It's fairly big against the full moon, but if any of you have seen it through a telescope, I'm sure this is what you've seen, because you need a long exposure to get much detail. Another one that Chris showed, the Sombrero Galaxy, very edge on, but you can see how thin it is. It's very, very thin. So these are called disk galaxies for a reason, because they look like disks. And we could also have these spiral galaxies with a big bar across the centre. Nobody quite really knows how these bars form, but they do form. We see a lot of them with them. They seem to spontaneously form in simulations of galaxies, but we're still not quite sure exactly the mechanism around those. This is the best model of a spiral galaxy. It's an egg, a fried egg. You have this bulgy bit in the middle and the yolk all spread out. And it's about this sort of dimension. If anybody still uses DVDs, it doesn't work quite so well with Spotify, but if you have a DVD, the thickness of the DVD to the width is about right for a galaxy. So you can see, really, spiral galaxies are very, very thin for their size. And this is what we talk about. The bulge is the centre, that's the oldest part usually. The disk, where we sit. The halo, where there's a lot of rubbish floating around, globular clusters, the odd star, and so on. And it all sits in a huge dark matter halo, which is about 10 times the size of the visible galaxy, if you believe dark matter. I know some of you are perhaps on the fence, but as a previous speaker said, about 99% of astronomers strongly believe there's something, that dark matter exists, if only we knew what it was. I got an entire talk on that. Back to galaxies, so this is M81. You can see the centre there, and more spirals. This is one you can do at home, especially over Christmas. This works really well, except people come along and eat it. And this is actually a composite one, but it does show you something rather nice. It's called a flocculent spiral because it's got many, many of these arms, so it's a very woolly spiral. But the key bit from the science takeaway is that the centre is very red and the outside is very blue. And to understand that, you just have to understand a bit of stellar evolution. So the sun, being one solar mass, about 6,000 degrees, looks kind of yellowish, whitish to us. If you go to a smaller star like a red dwarf, they are very red because they're a lot less hot on the surface, so they're giving out most of their radiation in the red. And the blue stars, being huge, give out a lot in the blue because blue is a much shorter wavelength. But the key thing here is that blue stars, you can see, last a very short time. So red dwarfs, 100 billion years, 100 gigayears, which is, this is the age of the universe. So lots and lots of red dwarfs around and will be for lots and lots of time. The sun somewhere in the middle, but these blue giants, a few million years, 15, 20, 30 million years, casually toss those figures around. But, you could have had two blue giants form, live and die since the dinosaurs were born, so they go through very quickly. But going back to the galaxy, you can see all this blue stuff here is given by those blue stars. So this tells us something here. There's a lot of blue stars there. Blue stars don't last very long, and this galaxy is at least, 12 billion years old. So we know this is making lots and lots of new stars in these arms, and that's where the blue colour's coming from. It's making lots and lots of different stars. It's making red ones, yellow ones, and blue ones, but the blue ones being so bright, they just dominate, and you see just the blueness. And in the centre, we see lots of red stars because nothing much is happening there, and it's just the old stars are just settling down and doing not very much. You can see here another one, whirlpool, with a few lines here. And the other nice thing about spirals is they're very well ordered. All the stars are going around more or less in the same direction, and they're all behaving nicely. You can get spectra of these things, and you can work out how fast they're rotating, because like these stars are coming towards us, those stars are all going away from us, and you can get a nice idea of that. And for the Milky Way, it's about 250 million years to go around once. So when we come back to this point, 250 million years, Brexit will be solved, we'll be over the pandemic, all sorts of things will be sorted out by then. So that will be great. In contrast, the ellipticals, which they're usually bigger and more boring than spirals, they're just this blobby mess. They're not like the spirals at all. They are very three-dimensional. So this is much more like a rugby ball or a football. It has depth as well as breadth and width and height. And the other thing about it is the stars are just very chaotic. They're not going around together. They're just all going around the centre in whatever direction or speed or whatever they wish. So astronomically, when you're looking at these things, there's not a lot you can get out of it. You can't say how fast it's rotating because the stars are just going sort of haywire. You can get a sort of a root mean square of the velocity of the stars, which is sometimes used, but they haven't got this nice ordered property like the spirals. This is an E5, so the number after it is how squished it is, how elliptical it is. So an E7 is very, very elliptical, and E0 is spherical, basically. So there's an E0, Hubble, F89, a nearby star, a nearby galaxy rather. And this is an E7, that's about as stretched as you can get. Theoretically, you could have an E8, an E9, an E10, but actually they seem to just fragment if they stretch that far. There's only so far you can stretch a bunch of stars before they snap. And this is the lenticular, which Chris also mentioned, or called S0s. And you can think of these as kind of spiral galaxies that have given up. So they're no longer producing new stars. They've given up producing stars, and so they're just going sort of red, but they're kind of disk galaxies. Much like this one here, it's all the sense of the spiralness has disappeared because it's just not bothering to make new stars. So somehow it's lost all that cold gas out of it, and it can no longer make any new stars. The Milky Way, incidentally, makes about one new star a year. That's about the average. It takes a few million years, to make a new star, but if you sort of average it out, it's about one new star a year. So this is another one that Chris had, M82 irregular. We always pick the nearby ones because they're nice and we've got nice sharp pictures of them. So this is the main galaxy, this is the outflows from it. So this is classed now as irregular because there isn't much structure to it. You can't really put that in any of the bins, so that goes in the the bin for anything that we haven't got a name for. And it's also a starburst because it's making lots and lots of these new stars, something else that Chris mentioned. So this might be making 200 to 300 new stars a year, so it's going crazy for a while. But if we come back in a gigayear or something, gigayear being a billion years and about the time anything interesting happens to a galaxy. So in about a gigayear this will perhaps have settled down to be something more recognisable. The other type of irregular galaxy we get quite a lot of is the dwarf irregular. So these are smaller galaxies with just a few, maybe a billion stars or a few 100 million stars, but they tend to be hanging around bigger galaxies. So they never really get a chance to settle down into, whatever they were going to be. They had all this energy when they were growing up, and they knew what they were going to be, but they're getting bullied continually by the bigger galaxy that they're going around, so they're getting stretched out of shape and so on. And we know that because the Milky Way snacks on these sorts of things every so often. Every billion years or so it eats one of these for breakfast. So, in fact, it's halfway through eating the Sagittarius dwarf galaxy at the moment. So its time has come. The Magellanic Clouds are also dwarf galaxies that are kind of irregular. Some people say they can see structure in them, but their time is, they've got about 1 billion years left before the Milky Way eats those up. So that's it. That's everything you need to know about galaxies, the main types. But there are these active galaxies, again, something that Chris hinted at. It started with Carl Seyfert finding these in the 1940s. He looked at galaxies and said, I see something odd about some of these. They've got a very, very bright centre here. This is much brighter than most of the other galaxies I've looked at, so what's going on there? And he wrote a paper about them, and they became Seyfert galaxies. And they're a class of things called active galaxies. So that's the Seyfert galaxy. And after he published that, somebody said, well, we found something else that looks a bit like it, but not quite the same, so we call it a Seyfert type 2. And then somebody found some that looked halfway in between, so they're Seyfert type 1.5s. And we're really, really bad at naming things in astronomy, very large telescopes, magnitudes and things like that, so Seyfert galaxies. And this is another one that Chris showed you with this radio lobes. And if we go back, this is 100,000 light years to go from one side to the other. So this jet is many, many, many light years long. So it's been shooting out for millions of years, and it has to be extremely powerful. You've got, no good pointing it out, is it? Pointing this. It's got, nearly 1 trillion stars perhaps in there, so that's a lot of gravity to shoot stuff out against, but it seems to be doing that effortlessly for millions and millions of years. So this was another active galaxy. This is another one, Centaurus A, also shooting stuff out. Then we found these things called quasars that nobody quite understood for a long time. They looked like stars because they were kind of single points, but eventually there's a whole story around that in itself. They were found to be about half the universe away, so they're obviously extremely bright, but there's one with the bit masked out, and you can see there's a fuzzy galaxy behind it. So these are actually the centres of galaxies. This is a very bright galaxy. Extremely useful for astronomers because you can see them for so far away. And then there's things called blazars and BL-lacs, and I used to know the difference between them, but I couldn't tell you what it is now. But if you're really into that territory, then there is a subtle difference between these. There's also radio loud galaxies, radio quiet galaxies, broader line radio galaxies, narrow line. Anyway, it's kind of depressing if you're a student having to learn all this, because you've got this sort of active galaxy, that, and the line seems to get ever longer. So come the exam, you're in a complete panic as to, are they going to ask me about BL-lacs, or are they blazars or quasar? But luckily, they all have a very common story. They are all powered by these things called supermassive black holes at the very centre of them, and this is what's causing all of them. And they're all just variations of the same thing. So once you get this concept into your head that they're actually all variants of the same thing, and it's just really the different ways we're looking at them, then it becomes a lot easier to answer exam questions on them, for instance. We've even got pictures of them now. This is the bigger one. So this is what it looks like. There's a big black hole at the centre, supermassive black hole, from a million solar masses up to a billion or beyond solar masses. It has an accretion disk, which is the water sort of going down the plug hole before it goes in the plug hole. This is what's powering everything. There's a lot of energy there as stuff goes faster and faster. This stuff is going round the black hole at nearly the speed of light before it goes in and disappears forever. So it can power a lot of stuff. And then there's also what's called the dusty torus right around it, this big donut thing. And so that stops you seeing some of the fine detail if you happen to be over here looking into it. Whereas if you're over here looking into it, you can see all the detail. So if you're looking down here, you see a quasar. If you're looking down here, you see a blazar. If you're looking from here, you see a Seyfert type 1, Seyfert type 1, Seyfert type 2, radio. They're all explainable by the same thing. And the only difference really is whether they have a jet or not. So some of them have this big jet that turns into a quasar, and some of them don't. And the jets seem to be, they last for a few million years and then seem to shut off. Not that we've actually watched one for a few million years, but that seems to be the trend. And that's really all that's happened. Our own Milky Way has one of these big supermassive black holes, but it doesn't have a jet, because that's lucky. They are extremely, extremely powerful. I used to do a calculation, actually not on this board, actually on the board on the lecture theatre behind us. So if you had one of these quasars out at the orbiting at the Sun at Pluto, so 40 astronomical units, and the jet was pointing at the Earth, it would boil all the oceans, which we know from this morning are about 4 kilometres deep, in about 1.5 seconds. You can do the calculation. So that is pretty catastrophic for life. So good job we don't have one of those as our Sun. It's probably less dangerous because we're halfway out of the galaxy. So, but anyway, luckily ours is very quiet and not doing anything. We also have collisions, which Chris mentioned. They're very boring to look at because we get like snapshots, so it's almost like one of those flick books where you flick through and you can sort of see what's happening. The antenna galaxy, which he also had. And then I've got a collection of stuff that I didn't know where else to put, just because it's galaxy related, and I kind of think it's interesting. So the largest galaxy, which is not this one, this is a spiral galaxy. Spiral galaxies are usually smaller than that. So if we shrink it down to this size, this is the largest galaxy. Catchy name of IC 1101, so if that comes up in a pub quiz, you'll be right there. This one was discovered by Simon Dye, who sits around the corner from me in an infrared survey. So this is the Darth Vader spaceship, clearly visible, as is the Lightsaber galaxy, which unfortunately is only visible in infrared. If you look at it in optical, it doesn't look like a lightsaber at all. Chris mentioned this one. This is GNZ11, the furthest galaxy, at about 13.4 billion light years. So 13.8 billion light years is the Big Bang, so this is pretty early. Except it probably isn't now, because there's a new kid on the block called HD1. Catchy name again, we're nothing if not. 13.27 or 13.5 billion years. So a long way back. There's still some argument about this because it was only about April, and it takes a long while for people to give up their favoured chalice and say, actually, no, you are winning this competition. There's also things called ring galaxies. Nobody's quite sure how you make these, so we sweep them under the carpet and just move on. There was a paper recently on perhaps an idea of how you might make them, but there's only a few of them around, so who cares really. Another common thing we talk about is the BCG, which is not something by Roald Dahl or anything like that. It's the brightest cluster galaxy, because yet again we are very good with our names. And this is the brightest galaxy in the cluster of galaxies and tends to sit at the centre and mess up everything around it. So other galaxies come by it and get chewed up by it. So it's a bit like the Magellanic Clouds and our own Milky Way. It occasionally eats them, but this one eats big galaxies for breakfast. And there's all sorts of statistics about this. Chris did quite a lot of work on this, in fact. This is something he didn't mention, so great, I've got something new here. This is lurgs, U-lurgs and E-lurgs. Anybody know what a lurg is? Anybody like to guess what a lurg is?
Large.
Not large.
Luminous.
Luminous, I heard infrared, yeah. And G, anybody?
Galaxy.
Galaxy, oh yes! So, luminous infrared galaxies. So, these are galaxies that look very boring if you look at them in a regular optical telescope. But if you look at them in an infrared telescope, they're extremely bright. So, naturally, we came up with the catchy name of luminous infrared galaxies. And then somebody said, oh, there's a whole class of these, so we make a big catalogue of them, and here's all the luminous infrared galaxies. But then there's another class that seem a lot brighter, maybe 10 or 100 times brighter. So we'll call those ultra-luminous infrared galaxies, because we're so clever at naming things. So there's the U-lurgs and lurgs, and then there's another class even brighter, which are the extremely luminous infrared galaxies. I'll come to that. Why are they infrared? So I just say that there was a possibility of a hyperluminous infrared galaxy and a few other oddities, but I don't think those are really caught on, which is lucky because we're really running out of adjectives at this point for at least clean ones that you could print in papers. So why are they luminous and infrared? So these are things Chris talked about this dust stuff that appears. So stars make a lot of elements. They make a lot of carbon, which comes out as dust. So we get a lot of dust in galaxies, but it's not really like your household dust. You can't hoover it up. It's much more like smoke, just sort of drifts around. But these are making a lot of that stuff. So we get a lot of carbon and silicates, sort of sands and silicons, floating around, and they just block out the light. So that's why you don't see them in visible light, because not a lot of light gets out of there. But you can't destroy energy, so these grains soak up this light and they start to get warmer and warmer, and then they start to glow in infrared. So what you're seeing here is a kind of shielded galaxy covered in dust, and we're just seeing the bit that comes out. Or it could be aliens. It could be a Dyson sphere, if anybody knows what one of those is, where you class it. It would be pretty sophisticated aliens if they can wrap their whole galaxy in a carbon nanotube of them. This is the part that Fraser and myself do. I have to say Fraser does it more than I do these days, certainly. But simulation. So maybe 2/3 of the department use things like this, which I'll come back to. Some of them do this, and this is actually very tame compared to what some of them, because we share the building over the car park with particle theory. And I don't know if I got it. No, I haven't got it. Let me just get rid of that. Let me just bring that up, because I think this audience might appreciate it. Most audiences do. So this one here. So this is a typical particle theory seminar title and abstract. Now it all looks, it's all English. These are all real words. Well, most of them are. But the more you read, the heavier your headache gets until you get to the bottom. And I've attended a few of these talks and thinking, oh, there'll be a nice introductory slide and I'll suddenly understand what Lagrangian Stuckelberg formations are or something like that. No. They start at this kind of level and they go deeper. And we're getting people chiming in with questions about general relativity and stuff, and you're thinking, oh, I wish this would end. So this is great when we're all on Zoom and Teams, because you could just click. No, I'm not getting anything out of this apart from a headache. So, but when you're at the back of the class and the door is at the front, it's pretty
What is an EFT?
Yeah. I'm surprised you even asked that in this. So this is what I use. So in fact, I don't use this anymore. This is the previous large computer in the university. It used to be in the building just across the way, but then they moved to another campus. So this was about 2,600 CPUs, and you could run simulations of the universe on it. I could knock out a universe in about a day on one of these. So Sometimes I'm saying 7 times better than God. I don't know. That's probably not right. Mine didn't really have the fidelity of the current one. There were no planets, there were no stars, so it was all dark matter. But there you go. The red things at the back are actually that's kind of the most interesting thing in there. That's a big canisters of halon that if it all catches fire, it douses the whole thing in this halon gas, which snatches away all the oxygen.
Does it let you get out?
No. This is far too valuable. I think you do get a warning. Anyway, best of my knowledge, it's never been used. So this is the simulation. This is, in fact, over here we have Fraser's F equals GMM over R squared, Isaac Newton's. Really simple equation to work out, especially with simulations, because in simulations all our masses are basically the same. So you can just say they're 1. So mass 1 and mass 2 are basically 1, so that's an easy calculation. You can also make G1 by nefarious mechanisms, so this all comes out to 1. And it's only the distance between things that you really have to calculate. And that's pretty simple if you've got 2 things. In fact, it's trivial if you've got 2 things. It's analytic. You can work out where you'll be any time in the future with 2 things. With 3 things, it's not possible. This is the 3-body problem where everything is pulling on everything else. So you have to creep up on the problem. You have to do a small step, recalculate everything, do another small step, recalculate everything. And we don't usually use 3 particles either to simulate a universe. We usually use about 1 billion to 1 trillion particles because you want to understand what's happening in great detail. So that's why you need a huge computer to do these billion calculations between all the particles. We don't actually do particle 1, how are you affected by particle 2, particle 3, particle 4, particle billion. Particle 2, how are you affected? That's far too slow. So there are better ways of doing it. But even so, it's a very expensive operation, which is why you need these huge computers to do it. Luckily, as they said earlier this morning, everybody has this picture. This is the pie chart of the universe. So this is the stuff we understand, and this is the stuff we don't understand. Dark matter is great to do simulations with. It doesn't bump into itself, it doesn't radiate, it doesn't do any of those nasty things that regular matter do. So you can take a huge number of approximations. It's very like having 2 galaxies come together. They just pass through each other. It never runs into each other, or hardly ever. So this is why you can run simulations so quickly on this. You don't have to account for all the nasty stuff that real physics does.
What shape do you invent with dark matter?
What shape? It's always purple. No.
So what shape? Do you make it spherical?
No, we make it a big box, but it's a special kind of box. Has anybody played asteroids in the past? So if you go off the top in the game of asteroids, you come on the bottom. So the box is wrapped around on itself in 3 dimensions, so you don't get strange things happening at the edge where suddenly the universe ends and there's nothing on the other side. So we kind of wrap it around on itself. So yeah, it's usually a big box, 25 megaparsecs big, 50, 100. How big's your computer is the question, to how big you make your box. And this is another one that Chris showed you. This is a later version. So every dot here is basically a galaxy. So we're sitting here and you just plot a dot for every galaxy you see on the way out. Because we can measure distances to galaxies relatively easy. You can't measure other things particularly well. And the dairy Lee bits missing are because this is looking into the galaxy and out of the galaxy. So there's lots and lots of stars here and dust, which is rather difficult to see through. People have done sort of infrared surveys now that look through that stuff. So it does look much the same. And that's the sort of structure we try and get with simulations. And here is one of the simulations I ran on the computer that used to be there in about 24 hours. So it starts off as this very fuzzy stuff soon after the Big Bang. And this is the 3-dimensional, and this is the 2-dimensional. You can see everything just falls into itself. Gravity is always attractive. There isn't any repulsive gravity as far as we know. So everything just collapses in on itself until something stops it, which Chris mentioned, feedback processes. So if there wasn't that, everything would just collapse in on itself. But we get stars form that have outward pressure, we get black holes that do stuff. And we end up with this. So this is 125 megaparsecs by 125, and also into the screen as well. So this big knot here is a huge cluster of galaxies. There may be 1,000 galaxies in this cluster all orbiting each other. You can see these sort of strands where galaxies drift along and come into this big cluster and heat up things. This is one of the voids they were talking about, hardly any galaxies in that. And if we take a snapshot of it, so this is the big galaxy cluster, we'd be somewhere out here, back in the outwaters, nothing interesting happening, just two galaxies out there that's not very much going on.
Julian, just to clarify, you're using dark matter, the halo, as a proxy for the galaxy.
Exactly, yes. In fact, yeah, there's no galaxy at all whatsoever in that. It's just a big density of dark matter. But for various reasons, dark matter forms first, or clumps together first, because it has about a 380,000 year head start on regular matter. So that forms, and then all the gas and stuff falls into that, and it makes that. So there are techniques for taking this and populating it with galaxies. It's not kind of real, but you can sort of paint them in. There are semi-analytic models where you can paint them in using some maths. Or we can do what's called the full physics, where you actually put matter in to begin with and you watch how the matter goes. But whilst we can run a good-sized dark matter simulation in a week maybe, to do a full gas run physics is like 3 to 4 months. So you've got to be really sure that your code is going to run for 3 to 4 months first. You've got to be 3 to 4 months of supercomputer time and so on. So it's a lot harder proposition. There's lots of them being done, but they're hard to do.
So do you end up with things like the great attractor?
Yeah. So this would be a great attractor because there's a huge amount of mass here. So this is sucking stuff down these sort of tubes. You can sort of see these filamentary structures. So yeah, stuff gets funneled down those into there, and we're doing quite a lot of research. In fact, I'm going on a research trip in 2 weeks to look at some of the effects of this, exactly what happens as these things come in here, what happens to the galaxies from simulations, and then we can say, well, we think this is what's happening, and you ought to be able to see this sort of thing if this is really happening. So then we turn to our visual astronomers and say, you should go and have a look in this sort of area for this sort of effect because we predict that's going to happen. And they come back and tell us, no, it doesn't. So we say, oh, yeah, it's a bug in the code, line 32, divide by 0, no wonder, yeah. So that's life in the simulator. So we're really pretty good at doing this large-scale structure, which is dark matter only. So this is the real data, this is the simulated data, and it kind of looks almost identical. I mean, it's not going to be identical because we don't have extremely good starting conditions, but all the same structures and the same sort of amount of clumpiness and voidiness appear across both of them. And we can also do much more basic simulations. So this is one done by Volker Springel, who's an absolute genius at this. This is gas, this is not stars, but this is like two spiral galaxies, just looking at the gas. So we can't see any stars in this, we're just looking at how the gas is. And the gas is very important because that's what makes new stars. So you can see as they hit each other, they sort of swirl around. Oh, and the colour is how hot the gas is. As Chris said, really hot gas, red, will not make stars. So the blue gas will nicely make stars. But you can see, you perhaps can't see, I can see on here, this is starting to get very red. So there'll be a big burst of star formation. We'd make some of these huge stars, these massive ones. They would go supernova very quickly and explode and blow gas out of things. We'd also get the black holes. They would probably go into this quasar mode and start having these jets shooting matter out. So you can see from all that gas that was there, a lot of it has shot out of these galaxies. And this would no longer be making stars. So if we could see the stars here, they would all be red and kind of given up. So this is one of the mechanisms we think that switches off that star formation. When you get this collision, you get so much turbulence and this explosive stuff that these elliptical galaxies, as this would be by now, just really don't have any material left to make new stars. And what is left is really, really hot. So you would see this in X-rays. So there just isn't the raw material available to make new stars. And I'm probably sure you've seen this one before. So this goes back many years. I think it was NASA who did this. So this is just our local universe, the Milky Way, and the local stuff. So Andromeda over here, and the Triangular Galaxy, which is somewhere between a dwarf and a real galaxy. But at about 4 billion years, it comes smashing into the Milky Way. And we don't think any of the stars will hit because, going back to the marble in Nottingham, marble in Calais, they just sort of go through each other. But the gravity just wrecks everything, really. It pulls stars out. There'll be stars ejected from these, never to return. They'll go crash, bash, bash. So about 4 billion years, if you want to mark that in your diary. But you'll probably have bigger problems because the sun will be going out about then as well. So it's not a good time to be around. Triangular Galaxy is also going to be chewed up with this. But what you can see is what started out as 2 lovely spiral galaxies is now a complete train wreck as these things have hit each other. And it's just higgledy-pigglediness. From the previous one, they've probably ejected all the gas, so they can no longer make new stars, so they're not going to look very blue or spirally. So that it's just going to be an old folks' home for stars at this point. They're all just going to sit around knitting, basically, till the end of time. So that's everything I want to tell you about galaxies. I'm just going to finish up with a few open questions that we're still looking at. Black holes. We now got pictures of 2. We've got our Milky Way and M something. I can never remember the number. 87. I knew it was in the 80s, but that's all piffling detail. Just like constellations. Like you ask an astronomer what a constellation is, they've got no idea. They know this tiny little bit of sky and nothing else. So, how do you make a supermassive black hole? Anybody know? There's a Nobel Prize in it? No? Okay. Nobody knows how to make a supermassive black hole. Well, that's not true. There are some ways you can make one. We know how to make a regular black hole. We know how to make one of about 10 solar masses, maybe 50 solar masses, something like that. If you get a really big star collapse, you can make one of that. But this is 1 million. So you need a lot of 50 solar mass stars to make one of these. And you also need, stars are all around the galaxy, many, many light years apart. You need to get them all in the same place. So that's pretty difficult. And the other problem is, we know from looking with very distant surveys like the ultra deep field from Hubble and others, some of these very, very early galaxies have these like quasar mode things. So they're extremely bright quasars, and that's just a few 100 million years after the Big Bang. So not only have they formed them, they form them really quickly. And there is a limit to how fast you can throw stuff into a black hole. You might think, well, they're the ultimate vacuum cleaner, they just suck in everything. But no, the more stuff you throw at it, the more it spirals round and generates this heat and so on. And that gives you a pressure that pushes outwards. So then it's much harder to throw stuff in. And eventually, the stuff coming out of it's not the black hole, but the accretion disk around it is pushing out as fast as you can throw stuff in. So that's called the Eddington limit, and it stops it accreting any faster than that. So even with that, if you have a black hole and you give it all the food possible, there is still a limit to how quickly it can eat it. And maybe in perfect conditions it could do that, perhaps in a reasonably quick time. But every galaxy we look at seems to have one of these, and it's grown very large. And okay, that's an open question. So if any of you on the train back, well, no, it won't be a train back because they're all cancelled. Any of you on the walk back want to quickly note down how to make that, then that's what. Another thing we're looking at, we're not looking at that previous one very much at our department. One we do look at is this one. So if you plot all the galaxies on this, so low mass to high mass, blue colour to red, you get these 2 clumps. So you get the blue cloud, which is basically the spiral galaxies, then you get the red sequence, which is all the ellipticals. These are redder than these, and these are typically quite a lot heavier than these. So these could be about 10 times the mass of these. So the question is, if we think these turn into those, does it go this way or does it go that way? Does it go redder and then get heavier, or does it get heavier and then get redder? And so we sometimes look at this bit in the middle called the Green Valley, where there aren't many galaxies. So that could be where they're making that transition. So there's a lot of people trying to look at those and see if they can work out what sort of things happen. How do you shut off star formation so they become red? And how do you add the extra mass to these things? Where does all that come from? Another thing there to be considered is to throw away that Hubble tuning fork diagram that I showed you very early on, and Chris showed too. And this is the cone model of galaxies. So instead of looking at types and what they look like, this is looking at how fast they rotate and number of spiral arms. So these are the slow rotators, these are the fast rotators. So these are supported by kind of pressure, and these are supported by spinning quite quickly. And these have spiral arms, and these don't quite so much. So that's another classification that trying to think who proposed it. Oh, Atlas 3D. There we go. It's even on there. The cone model, because it looks like one of those cones that you have the handle and the cone bits on it. So that's a new idea that could replace Hubble, but we're kind of stuck in the mud in astronomy. We always go back to magnitudes and classifications and early type and late type. So probably not, but good of them to try. Forward to tomorrow. This is, anybody know what that is? Gaia, there we go. Yeah, so that's the Gaia satellite mapping the Milky Way. So we'll have about 1 billion data points for the Milky Way. Lets us load that into a computer and make really good models and predictions of the future, such as this one. This is done by ESA, who are running it. So this is looking at, they took all the stars that Gaia captured and did a sort of SQL filter on it and said, which ones are going really, really quickly? And it turns out to be these ones, and these are going far too fast to actually stay within the Milky Way. So they've either come from elsewhere and they're just passing through on a road trip or something, or possibility is that it's some interaction with the supermassive black hole. If they get too close to that, then they get into this thing, a bit like Fraser said, and they get kind of flung out at high speed. You need 3 things interacting. You need the supermassive black hole and 2 stars, basically, to do that. James Webb, our next favourite spacecraft, as soon as it starts producing data. Chris says he's getting it in a couple of weeks. There's a couple of other people in the department also hoping to get early data to do stuff. That star picture he showed with the galaxies? Yeah. They published that as a JPEG intentionally, because if they published it as a PNG or a TIFF file, the astronomy community would be all over it, getting the data out of it. But because it was this hazy resolution JPEG, there wasn't enough detail in there to actually do science on it. So that's the reason it was published like that. The Square Kilometre Array, this is this big radio telescope starting to come about in South Africa and Western Australia that will bring things about. Everybody know what that is? Extremely large telescope, because we're very bad at naming things. Very large telescopes, Arc de Triomphe, not a telescope. ELT, 39 metres, going to be a fantastic thing. It says 2025 there. I think it slipped a year or two. Mike Merrifield tells me it slipped of some money as well. But they're struggling to get enough money together now because of issues around the pandemic and having to pay people and so on. So they're going around cap in hand. They've had €1 billion and they want a few more. Oh yeah, it's up to about this level, I think, somewhere about there. They've leveled the base. They have this big video of blowing the top off the mountain, which we all tuned into, and it's going to be, there's like 5, 4, 3, 2, 1, and there was is that it? So anyway, apparently it was enough. They leveled the mountain, they poured lots of concrete, and so they're up to about this level here before they put the optics and stuff in. 2026, 27 probably, this will be producing data. And this is what a 40-metre mirror looks like. This isn't the 40-metre mirror, this is cardboard, but because you wouldn't do that with your mirror, would you? You need to clean it afterwards. But just to see it. So just to wrap up, galaxies are really big, say about 400 billion stars in a galaxy, say a good fraction of those have planets. So there's more than enough for several planets for everybody in the world, many times over. And if that's a problem, there's 2 trillion galaxies, each of those with those sorts of things in, so there's lots of room for expansion. We're still continuing to do research. I don't know if any of you have been involved in research, but it's a very, very slow process and very incremental. Nobody suddenly goes, Eureka, I've solved it, or very few people these days. But new telescopes like the ELT, James Webb, SKA, ALMA's been around for a bit now, but there are other ones. There's the 30-metre telescope and the GMT and others that are all being built, and new space telescopes too that will help. So with that, thank you very much for listening. I forgot whether I've outlived my time or not, have I?
Thank you very much.